So let's talk more about buffers. For most solutions, if you add an acid or a base, the pH of the solution will change significantly. Buffers reduce or resist the pH change. So what's a buffer? A buffer will contain significant amounts of a weak acid and its conjugate base, or a weak base and its conjugate acid. If you just have the weak acid or the weak base alone, there won't be enough of the conjugate to act as a buffer. So here we have an illustration. A solution of a weak acid. The weak acid can neutralize base that's added to the solution. The conjugate base, which is typically something like a sodium or potassium salt, so acetic acid, the conjugate base is acetate ion. So this could be added as sodium acetate. The conjugate base is a weak base, and so it can neutralize added hydrogen ions. So when we mix those together in the buffer solution, we have significant amounts of the weak acid intact, the acetic acid, and the anion, the conjugate base, the acetate ion. We also have hydronium ions and sodium ions. And so if you add sodium hydroxide to this, the acid will neutralize it. And if you add base to this, if you add, I don't know what I said, so I'm going to start over. If you add sodium hydroxide, the acid will neutralize it. If you add acid, the base will neutralize it. It's really kind of a cool concept. So here's a conceptual question identifying a buffer. Which solution is a buffer? What are we looking for? A weak acid and its conjugate base, or a weak base and its conjugate acid. So all of these choices have HNO. Oh, I'm sorry, that one doesn't. We've got HNO2 and HNO3. Which of these what are these, weak or strong? This one's strong. So here we've got a strong acid and its conjugate base, but that's not going to do anything. So that's no good. What about A, C, and D? Those have a weak acid. What's the conjugate base of nitrous acid? NO2. Nitrite ion. So does this have nitrite ion? No. Is this one? No. Is this one? Yeah. This is the conjugate base of this weak acid. So that's the answer. Any questions?
What qualifies as a significant amount of the conjugate base? Does it have to be the same?
That's a great question, and we will discuss that in a minute, but roughly equal. If I remember correctly, it's like less than a 10% difference. So here they're equal, and so that's excellent.
So it has to be the conjugate base of the weak acid.
Yes, it has to be a weak acid and its conjugate base, or a conjugate base and its weak acid. I mean, you know what I mean.
Yeah.
They both have to be weak, yes. Because if it's strong, it won't reform the molecule. It'll just stay dissolved. So, if we look at this equilibrium, here we have acetic acid in equilibrium with its anion, acetate. And if we start out with 0.1 molar acetic acid and 0.1 molar sodium acetate, how does this affect this equilibrium? Well, we're starting out with this being 0.1 molar and this being 0.1 molar. So if we started with just acetic acid, this equilibrium or this ionization would happen more because there wouldn't be any acetate ion present initially. Here we've added both of these, and so because they are both present, the acetic acid that's there will ionize even less than it normally would. This is called the common ion effect. This is, we've added sodium acetate, which has an ion in common with this equilibrium. Does that make sense? If we didn't have this, then we could make an ice table and we could figure out that, well, okay, this is going to lose, writing with the eraser, lose X, and this is going to gain X and gain X. So we could look at the Ka and figure out what the concentration is, right? And so some of this would ionize to form the acetate ion. If we start with acetate ion present, though, it will not, the acetic acid will not ionize as much. So, yeah.
It has to do with, because they're also in equal amounts too, in molarity?
Well, any amount of this that you add would affect this equilibrium and cause the acetic acid to ionize less than if it wasn't there at all. We'll see that maximum buffer capacity happens when you have equal amounts, but they don't have to be exactly equal. So let's look at this one and calculate the pH of a buffer solution. So this is 0.2 molar acetic acid and 0.1 molar sodium acetate, and we're given the acid ionization constant for acetic acid. So we want to start by writing the equation for the ionization of the weak acid. So we're going to get acetate ion. So here's our acetic acid, and here's our acetate ion, the conjugate base. And we can make an ice table for this. So initially, we have 0.2 molar acetic acid, so 0.200 molar over there, and 0.1 molar sodium acetate. So when we see this guy here, sodium acetate, that's a soluble ionic compound. And so that's going to dissociate into sodium ions and acetate ions. Does the sodium have anything to do with the pH? It doesn't. It's a spectator ion. Here we refer to it as a counter ion because in order to bring acetate and put acetate in there, it has to come in with a positive ion. So the sodium is just along for the ride, and we just kind of ignore it because it doesn't do anything. And then we can say that the H plus concentration is essentially 0 to start with. And then we can look at the change and the equilibrium. Now, which way do you think this is going to go? To the right, because there's no hydrogen ion essentially, and so it can't go to the left. So this will be minus X, X, and X. And then at equilibrium, we have 0.200 minus X, X, and 0.100 plus X. We can write our equilibrium expression, Ka, which here is 1.8 times 10 to the minus 5, will be equal to X times 0.1 plus X divided by 0.2 minus X. We could use our solver, or we could try X is small. I'm going to try X is small. So if X is small, then adding this X and subtracting this X makes no difference. And so then the math is actually fairly straightforward. 1.8 times 10 to the minus 5th 5 times 2. Oh my goodness. Don't remember how to talk. So using x is small, I get x is equal to 3.6 times 10 to the minus 5. To see if that's valid or not, I need to compare it to the numbers it was added or subtracted to. I want to look for the worst case, and so I'm going to compare it to the smallest one here, the 0.1. So if I divide that by 0.1 and multiply by 100, I get 0.036%. X is small. So X's small approximation is fine. So we found X, and we're all excited about that, and then we realized, oh, wait a minute, what was I supposed to find, and what does X mean? So X here represents the equilibrium concentration of the hydrogen ion. I'm trying to find the pH. So pH is the negative log of the hydrogen ion concentration, 3.6 times 10 to the minus 5. pH is 4.44. Any questions? .44. So we can always solve these problems using ice tables, but there's actually an equation called the Henderson-Hasselbalch Equation. So that's quite a mouthful. That makes this go a lot faster. It can't be used in all circumstances, but it can be used in a lot. So we can derive an equation relating the pH of the buffer solution to the initial concentrations of the components of the buffer. So we're going to use our generic acid HA. So we can write an equilibrium constant expression for this, where Ka is going to equal H3O plus times A minus divided by HA. And I'm going to rearrange that. I'm going to solve that for H3O plus. So the H3O plus concentration is going to equal Ka times HA divided by A minus. I multiplied both sides by HA, I divided by A minus. Okay? Now, I'm trying to find an equation that's going to give me the pH. Here I've got hydronium ion concentration, so if I take the negative log of this equation, the left side will say pH. So negative log of the hydronium ion concentration is equal to the negative log of Ka plus the negative log of HA over A minus. When you take the log of things that are multiplied, you add them. The log of Ka plus the log of HA over A minus. Yes?
Why would it be Ka times HA over log of A minus?
Because that doesn't give me anything useful. This is not the only thing I can do to the equation. Yeah. And this time I made notes so I wouldn't go off into crazy land. So this is equal to pH, right? So we can say the pH is equal to negative log of Ka is pKa, right? So that's pKa. And then here we're getting the negative log of HA over A minus. It's nicer if we don't have a negative there. If I get rid of this negative, I invert this fraction. So that's the same as plus the log of A minus over HA.
You could still do it, that negative is still there though, right?
You could. So this is the same as the log of A minus over HA. So the pH is equal to the pKa plus the logarithm of A minus over HA. This is easier for me to remember because in our equilibrium expressions, it's always the products over the reactants, right? And so it's A minus over HA, and here it's A minus over HA. And then I think life is just more positive without negative signs. Yeah.
What was
pKa is the negative log of the Ka. So it's the acid ionization constant, the negative log of it. Yeah.
How did you get from that step, the last two steps?
How did I get from here to there?
No, from there, the top, right, to down.
Okay, this was explaining how I got from here to here.
Oh, okay.
It's not really very clear. So I took this piece and I changed it into that. And I could do that because this is true. So this is just kind of an aside. Does that help?
Oh.
Any other questions? So this is one way of writing the Henderson-Hasselbalch equation. The pH is equal to the pKa plus the log of the base concentration over the acid concentration. This equation is useful as long as the x is small approximation is valid.
It's a conjugate, or,
These have to be
conjugate base of-
these have to be conjugates of each other. Yeah. They can't just be random weak acids and bases. They have to be together. So x is small will work if our initial concentrations are not too small and if Ka is fairly small. So the acid and the base, then I'm not sure what this means. Initial concentrations are not too small and K is fairly small. Acid and base greater than 100 to 1,000 times Ka. I think that's saying that these concentrations have to be larger than the Ka, like 100 to 1,000 times larger. The equilibrium approach to finding the pH always works, but this can be a lot faster. Any questions?
So this is just like unrealistic view.
Yeah. What's nice about this is if you use equal concentrations of the acid and the base, this term goes to 0, and the pH of your solution is equal to the pKa, no math required. Whoops, now I'm really lost. Okay, so if the concentration of the base and the concentration of the acid are the same, then this is 1, this fraction is 1, the log of 1 is 0, right? So then the pH equals the pKa. So calculating the pH of a buffer solution as an equilibrium problem and with the Henderson-Hasselbalch equation. So here it says to use both approaches. Calculate the pH of a buffer solution that's 0.25 molar in HCN and 0.170 molar in KCN and we're given the Ka for the acid, and we're also given the pKa, which we could calculate also, but it's just handed to us. Let's do the Henderson-Hasselbalch equation first. I'll do that on the right because the question kind of suggests that we should be doing that second. So the pH equals the pKa plus the log of the base over the acid. So the pKa here is 9.31 plus the log of, what's the concentration of the conjugate base? 0.17. And so this is the conjugate base, and this is the weak acid. And so the concentration of the acid is 0.250. So the pH is 9.31 plus the base 10 logarithm of the quantity 0.17 divided by 0.25. 9.14. Any questions about that?
Now, you say that we can only use this if X is small,
Mm-hmm.
or if the.
So these concentrations need to be like 100 to 1,000 times bigger than Ka, and they are. Because when X is small, the initial concentration of acid and base present is equal to the equilibrium concentration. Because adding or subtracting the X is small, and so it doesn't affect the concentration. Okay, let's do the equilibrium method. So we look at the equation for this acid. It's going to form H plus and cyanide. We'll make an ice table. The initial concentration of HCN is the 0.25. The hydrogen is essentially 0, and the cyanide is 0.17. And so then we look at how is this going to change. This is going to decrease by X, increase by X, increase. So at equilibrium, we have 0.250. That's too messy. 250 minus X. We have X, and we have 0.170 plus X. So 4.91, no, just 4.9, 10 to the minus 10 equals X times 0.170 plus X divided by 0.250 minus X. I'm going to do this one on my solver just because 4.9 times 10 to the minus 10, and we've got X times 0.17 plus X divided by 0.25 minus X. X is 7.2058 times 10 to the minus something minus 10. when it shows it to you, initially, you don't necessarily notice that there's an e to the something at the end there, and you're like, 7.2? That's not possible. Yeah, so you have to scroll up to it and then scroll over to the right until it shows you, oh yeah, e minus 10. Okay. So negative log of that. 9.14. What do you know? Any questions? Henderson-Hasselbalch equation is a shortcut that does this with x is small. Here I did this without using x is small, just to prove that this is truly the correct pH. And it comes out exactly the same. If you do it with x is small, you end up with the same thing too. Yeah.
If we're just given Ka, is there a way for us to quickly find Ka?
The negative log of it. Mm-hmm. That's a good question. So here, pKa, P means negative base 10 log of.
So the negative log of 4.9 times E negative
Yep.
9.1.
The negative log of 4.9 times 10 minus 10 is 9.30980392, which to 2 sig figs is 9.31.
Do you have to worry about counter ions that have an acidic character in these types of problems?
Most of the time you will not. I mean, that could come into play, but most of the time it's going to be like potassium or sodium or something that is pH neutral. Any other questions? So how do we calculate pH changes in a buffer solution? The buffer resists change in pH, but it does change a little bit. It's not a miracle worker. So to do these problems, we need to break it into 2 parts. The first part is a stoichiometry calculation, looking at how much does the addition change the relative amounts of acid and base. And then after we do that, we do an equilibrium calculation. And that's what we've become familiar with from chapter 17. A buffer contains the weak acid HA and its conjugate base A minus. The weak acid has a pKa of 4.82 and the buffer has a pH of 4.25. Which statement is true of the relative concentrations of weak acid and conjugate base? Are they equal? No, because if they were equal, the pKa and the pH would be the same, right? And they're not. The pH is actually lower than the pKa, right? Which is that more acidic or more basic? More acidic. So which do you think there's more of, the acid or the base? The acid. Yeah. So there must be more acid than base. Okay, here we're going to look at a liter of buffer, and it starts out being 0.1 molar in both the acid and its conjugate base, and we are going to calculate the pH after adding 0.025 moles of a strong acid to this solution. So the first thing is stoichiometry, finding out how much does the addition change the relative amounts of HA and A minus. And for this part, we need to do this in moles. We can't do this part in molarity. This has to be in moles. So here's our generic equation. We're looking at the acid reacting with the base to form the weak acid. Because we're adding strong acid to the solution. We're adding H+. If we add H+, is that going to react with HA or A-? It's going to react with the A-, right? So that's why we've written the equation this way. So initially we're starting with essentially 0 H+, 0.1 molar A-, and 0.1 moles of A- and 0.1 moles of HA. Because it's 0.1 molar in both, and we have 1 liter. 1 liter times 0.1 moles per liter gives me 0.1 moles. We're adding 0.025 moles of acid. And so this is going to react, and we're going to assume that it's going to react completely. So all of this reacts, ending up with essentially 0. That's going to reduce the amount of this by 0.025, and it'll increase that by 0.025. This is not an ice table. It's easy to confuse it with an ice table because it kind of has the same shape, but it's not. And it doesn't really have a name, but it's a ba table. Ba, like a sheet. Before addition and after addition. So these are the amounts that we're going to use in the second part of the calculation. So adding a small amount of strong acid is equivalent to changing the initial concentrations of the buffer components, and we calculate the new pH by working an equilibrium problem, either with an ice table or with the Henderson-Hasselbalch equation. So here we've set up an ice table. Here we have now the acid is 0.125, the base is 0.075. Yes?
Why did you subtract the 0.25 from one and add it to the other?
That's a good question. Why did I subtract from this one and add to that one? Because this is going to react with 0.025 moles of this conjugate base. And they are going to form 0.025 moles of the acid.
Does that all mean work with a strong acid?
It gets more complicated with a weak acid. So if I have 0.025 moles of H+, and I've got some A- present, how much of the A- is going to react with this? 0.025 moles. And they're going to form 0.025 moles of HA. And this goes to completion, and so I have lost, this is lost, and this is lost, and this is gained. So I had 0.1 moles of this and 0.1 moles of that, and everything was all happy and good. And then I add in some acid. The acid will react with the base. The base will neutralize the acid. That causes the base concentration or the base amount to go down and the acid concentration to go up. Anybody else still have questions about that? Because this is a thing that is hard to get. Yes?
The HA is the weak acid, right?
This is the weak acid, yep.
So even though there's more of the weak acid, it doesn't fully dissociate. And so, like, saves the...
So we have initially a lot of the conjugate base and the weak acid. And so when we're adding this strong acid, this is like HCl or something, and so it's not associating with anything. It's just straight old H+ coming in. This will react with this and form HA. Essentially, it's causing the ionization reaction of the weak acid to shift. That equilibrium is going to shift. But we can't look at this in terms of moles per liter, because when you add strong acid, that changes the volume. And so we need to be careful about that. When you have a solution that's just shifting equilibrium, it's the same volume, and so all the volumes cancel out. But this table has to be done in moles. So over here then we have our new amounts, and then we can calculate what this is going to do. You either use the Henderson-Hasselbalch equation or use the pKa, the Ka, and solve it using x is small or whatever's appropriate. We don't know what the acid is here. We don't know what the Ka is, so we can't actually solve this problem. We're just looking at how do you solve the problem. Yes?
These numbers are only the same because we had a 1 liter solution.
Right.
Back in
We had
that
1 liter solution.
Okay.
We can do this part in moles or in moles per liter. But if we do it in moles, then we just have to remember that what we're finding is the moles of H3O+, and then we have to look at the overall volume to find the molarity. But we can do that because when we're looking at moles and moles, the volumes are going to cancel out. If we add a small amount of strong base to a buffer, we have the exact opposite happening, where the strong base that's added is going to react with the weak acid. And that will form more of the A-. So here adding 0.025 moles of base will react with 0.025 moles of the HA, the acid. So that's reduced, and this is increased by 0.025 moles. So a summary of that, if we're adding a small amount of strong acid to the buffer, it's going to convert a stoichiometric amount of base to the conjugate acid, creates more acid, and it will reduce the pH. Makes sense. If you add acid to something, the pH should go down, right? In a buffer solution, that's still going to happen, but it's going to go down by much less than if it was unbuffered. If you add base, it's going to convert a stoichiometric amount of the acid to the conjugate base and cause the pH to go up. So here we have our initial buffer. We have equal concentrations of the weak acid and the conjugate base. So here's the weak acid as little purple and white molecules, and here's the conjugate base. It's the acid without the hydrogen ions. If we add hydrogen ions to this solution, the hydrogen ions are going to react with some of these and form more of the HA. So here we've got one less. Over here we had 4 of each. Here we have one less of the base and one more of the acid. If we add base to this, the base will react with the acid. We'll have one less acid and an additional base. Any questions? I'm pretty sure that this is one of those concepts that seems very simple and straightforward to me because I understand it, but it's not very simple and straightforward if you haven't studied it before, which you guys have not. You have both acid and base present. So if you add some acid to this, the base can neutralize it. And if you add base to it, the acid can neutralize it. And, it's all about, we want to keep things the same, right? It's an equilibrium, and it's trying to keep everything the same. Le Chatelier's principle, you do something to it, it's going to shift in a way to undo that. So it's trying to maintain the pH. It will change a little bit, but not very much. So this is a conceptual question. Looking at this diagram we were just looking at, which image best represents the amount of hydroxide that's added to the buffer in part B? So going from here to here, were we adding 1, 2, or 3 molecules of hydroxide? 1. Because if we add one of these, it's going to eat up one of those. I'm sorry, one of these. See, so take this guy. It's going to combine with one of those. So the acid from this is going to, the H plus from this is going to make water and A minus. So that one goes away, and then we form another one of these. No? Maybe I need to draw better pictures. So this is OH minus. And if I add HA to that, what do I get? H2O and A minus, right? So here's my hydroxide, and here's a very bad representation of this guy, the HA. So when these react, I'm going to end up with the A minus and a water molecule. Okay with that? So what's happened from here to here is that one of these has given up its hydrogen to neutralize the hydroxide that was added. And so it becomes just a purple one now, the conjugate base. And so here, this one used to be over here with the hydrogen, but it gave up its hydrogen to neutralize the base. It's sacrificing for that. And it becomes one of these. Now I have more conjugate base than I did before. Still getting some very puzzled looks. I have permanent frown lines from doing that. Ask a question.
I don't even understand what you're asking in the question. Which image best represents the amount of each added?
Okay, so the question is,
Totally lost right now.
let's get rid of that. So this is the process that's happening. Are we okay with that? If I put this one and this one together, the hydrogen from this comes over to this, makes a water, and what I've got left is A minus. We're cool with that?
Yeah.
So this is saying getting from here with these 4 of each to getting over here, how many hydroxide ions would I have to add here to make it become this?
Oh, that's what that's.
That's all it's asking.
Oh.
It's okay. Sometimes conceptual questions are harder than math questions because you're like, whoa.
Yeah.
Any other questions? Okay, so let's do a calculation. 1 liter buffer solution contains 0.1 moles of acetic acid and 0.1 moles of sodium acetate. Because the initial concentrations are equal, the pH is equal to the pKa, which is 4.74. Calculate the new pH after adding 0.015 moles of sodium hydroxide. Well, what is the sodium hydroxide going to react with? The acetic acid or the sodium acetate? I have hydroxide ions. it's going to react with the acid, right? The base is neutralized by acid. And what's that going to make? Water, acetate ion. So I'm adding sodium hydroxide. The sodium is just the mandatory date that hydroxide had to bring. It's a counter ion. It's just a companion. It's not actually doing anything. Along for the ride. So I have hydroxide ion. And the hydroxide ion is a base. It's going to react with an acid. So the hydroxide ion reacts with the acid to form water and the conjugate base of the weak acid. Yes?
Should there be a double arrow? Or
Should there be a double arrow? That is a great question. What we're doing here is we're not considering the equilibrium. We're considering that this hydroxide is going to react completely, that the buffer is going to neutralize it, and then we'll look at how that changes the equilibrium. Yeah, it's a good question. So this is the Ba table. So before, we have 0 hydroxide. Yes?
When we're doing the pH of a buffer, we do the bar and then the ice.
Yes. Yep. You have to. Well, if you're adding something to a buffer, if you're just looking at a buffer, then you just do the ice table.
Does the same go for a weak acid or base?
Yes. If you're adding an acid to, if you're adding a strong acid or anything you're adding, yeah.
We don't consider free water, right?
The water being a pure liquid doesn't matter. And initially we had 0.1 moles of the acetate. So then when we look at what's being added, so we're adding 0.015 moles of hydroxide ion. We're not adding any of this, we're not adding any of that, we're not adding any of this. After the addition, after this reacts, 0.015 moles of hydroxide will react with how many moles of the acid? 0.015 moles, right? So this will all get used up. If it helps, think of it as a limiting reactant problem. This is the limiting reactant. This is going to get all used up. And so this is 0 again. It's going to use up 0.015 moles of that. So we're going to subtract. So this is going to be 0.085 moles of that that's left. This still we're not going to worry about. And this is going to be 0.115 moles of that. So the hydroxide reacted with some of the acid to make more of this. And so we're going to assume it just reacts stoichiometrically, and then we'll do the ice table using these new amounts. Okay?
this is like the beginning to our equilibrium.
Yeah, we're going to use this for the beginning of the equilibrium.
Okay.
And I took up an awful lot of room doing that. So now we're going to look at the equilibrium. So our new initial is that we have 0.085 moles of that, essentially 0 of that, and 0.115 moles of that. So this is going to lose x, that's going to gain x, this is going to gain x. So we've got 0.085 minus x, we have x, and 0.115 plus x. Do you think the Henderson-Hasselbalch equation could be used here? Probably. So let's do that.
What would we not, like, what kind of number would make we not use? No one's
Well, x has to be small in order to use.
right, so it's like 10 to the negative 1, not small? What's small?
Well, so this is Ka here is 1.8 times 10 to the minus 5.
Right.
And so these concentrations need to be significantly larger than that.
Okay.
So our smallest one there at 0.085, if I divide that by 1.8 times 10 to the minus 5, is 4,700 times larger. So x is small, is going to work. So the Henderson-Hasselbalch equation, then we would just use these new amounts. We have to consider the volume, except that it's the same, and so that cancels out. So we've got pKa is 4.74 plus the log of the base concentration over the acid concentration. .87.
So did we only do the ice table to find out if X was small?
No. Honestly, I did the ice table out of habit.
Okay.
But then I decided that since I drew it out, we're actually going to solve it that way too, just because. So if x was not small, I'd have to actually do the equilibrium expression and use my solver. So I'm plugging that in. X is 1.33 times 10 to the minus 5. And when I take the negative log of that, I get a pH of 4.876. Which would round to 4.88, but essentially the same. And if I check the x is small, 1.33 times 10 to the minus 5 divided by 0.085 times 100, yeah, it's way less than 1%. Any questions? You can also make a buffer from the base and its conjugate acid. Things like ammonia and ammonium chloride calculations are going to be similar. When we're using the Henderson-Hasselbalch equation, though, we're still using Ka. So if it's a base and it's conjugate acid, you need to calculate Ka or pKa, and you can use this relationship, pKa plus pKb equals 14. In much the same way that pH plus pOH equals 14. Yes?
So if we're given a Ka, we just find a pKa.
Plus PKB 14 and solve for KB.
No. No. You would use this if you were given the pKb and you needed the pKa. You just subtract from 14. If they gave you the Ka, you just take the negative log of it, and you've got your pKa.
You don't use like KB, just the KB.
Right, you can't use Kb in the Henderson-Hasselbalch equation. It just doesn't work. So here we've got a weak base and the conjugate acid, ammonium chloride with ammonia. And in the buffer solution, we have significant amounts of the weak base and the conjugate acid. And so again, we can add acid, the base will neutralize it. We can add base, the acid will neutralize it. Use the Henderson-Hasselbalch equation to calculate the pH of a buffer solution composed of its weak base and its conjugate acid. So calculate the pH of 1 liter of a buffer solution that's 0.5 molar in ammonia and 0.2 molar in ammonium chloride when 0.1 mole of solid sodium hydroxide is added. And we're given pKb for the ammonia. Now, we could calculate the initial pH of the buffer, but we don't need to, and it didn't ask us to, so we're not going to. We're adding hydroxide. So hydroxide ion is being added. What's that going to react with? The ammonia or the ammonium? The ammonium, right? It's going to react with the conjugate acid. So we make a Ba table. Initially 0 of that. We have to do this in moles. We have 1 liter of solution. It's 0.2 moles per liter ammonium chloride. Since there's 1 liter, it's 0.20 moles. The water doesn't matter. And the ammonia is 0.50 moles. We're adding 0.010 moles of solid sodium hydroxide. And we're not adding any of these. So the buffer's going to do its thing and neutralize this so that we get back to 0 here. This is going to use up 0.01 of the ammonium. So we're going to have 0.19 moles of that left. And we're going to have 0.51 moles of this afterwards. So the concentration of the base is NH3, and that's going to be the moles divided by liters. It's 1 liter. And the concentration of the acid is NH4+, and that's 0.19 moles in 1 liter. Henderson-Hasselbalch equation, pH equals pKa plus the log of the base over the acid. What's pKa? Yeah, it's 14 minus 4.75. So pKa equals 14 minus pKb. Yeah. Any questions?
So just to clarify, you could not find POH by using PKB and then flipping acid and base?
I think you could,
Oh, okay.
but it would be confusing, so we don't talk about it.
Where
Any-
did you get the 50 from the table, 50 and 51? What did you get?
So this is the initial amount of ammonia. We had 1 liter of 0.5 molar, so that means I have 0.5 moles. And I added 0.01 moles of hydroxide, so that's going to react with 0.01 moles of this and make 0.01 moles of that, which will add on to this.
So you added the 0.20 and the 0.010?
This is 0.50 plus 0.01. And this is 0.20 minus 0.01. Yes?
So say we started with NH3 and added H, that would go, this would make this go opposite.
Yeah, if we're adding an acid, then instead of writing this equation, I'd write NH3 plus H plus, forming NH4 plus. This part is just basically to help us figure out, okay, what's getting bigger, what's getting smaller, by how much.
Just a easier way to lay it out.
Yeah. And I personally am not thrilled with these tables because you don't see there's no change factor in here, and then, like the question was, well, where does this come from? This part doesn't get written out anywhere.
I mean, you could assign a
We could make up our own table,
right.
but I've decided I'm just going to try to be consistent with what the book does, because in the long run it's easier. Anybody else have any questions? 9.68. Yeah.